In this video, we're going to go over some practice problems to get ready for the test on sections 5.7 and 5.8. And remember, 5.7 covered the natural log integration, and section 5.8 covered the inverse trig functions integration. And both of these sections, it's important for the pattern recognition. We want to take the integral that we're given and we want to fit it into a pattern. If we can squeeze it into the antiderivative of a function as the denominator and its numerator is that function's derivative, then when we integrate, we're going to get the natural log of the absolute value of that denominator plus our arbitrary constant. And for the inverse trig functions, remember we have arcsine, arcsecant, and arctan. If our integral fits into these patterns, this pattern becomes arcsine, this pattern becomes arcsecant, and this pattern becomes arctangent. Remember, there are some fundamental differences to look for. Arcsine and arcsecant both have denominators with radicals in them. Arcsecant has a little extra. It has this extra u out front of the radical. If we have something with no radical on the denominator, it's possible it will be the arctan function. Remember also the placement of the a and the u are critical. In the arcsine and arcsecant functions, we have a subtraction going on under the radical. In arcsine, it's our number squared first minus our function squared. In arcsecant, that's reversed. Our squared function is first minus our squared number. In the arctan function, it doesn't matter which is first because we do have a plus sign there. We could have u squared plus a squared or reverse it. It doesn't matter. So let's take a look at our first problem here. The directions say find the indefinite integral. We have a fraction, so it could be log. It could be possibly arctan. There's no radical in the denominator. But remember, in the inverse trig functions, the things in the denominators are always squared. You know, we don't have any obvious squares here, but we know that 4 is 2 squared. And we could write 3x as the square root of 3x quantity squared. That's a possibility. But it looks more like this is going to fit our natural log integration rule. Remember, we want to fit the pattern u prime over u. So if we let u equal our denominator, 4 minus 3x, the derivative of that would be negative 3. And in our numerator, we don't have negative 3, but that's just a constant. We could tweak our function. We could multiply in here by negative 3. And to balance that out, of course, we'd have to multiply the entire integral by a negative 1/3, the reciprocal. So now we do have it in this format. And just to drive the point home, I'll even write it with the full U-Substitution. So we are letting u equal our denominator, 4 minus 3x. So that becomes a u. What is the derivative of that? Du dx would be negative 3, and then we'd multiply both sides by the dx and get du equals negative 3 dx. We didn't have the negative 3 dx, but we were just a constant away. So now here is negative 3 dx. That becomes my du, or with the prime notation, u prime. So we're all set to go. And this, when we take the antiderivative, the negative 1/3 stays put. And then we'll have the natural log of the denominator, u plus c. And then we can plug our u back in. Negative 1/3, natural log of the quantity, absolute value, 4 minus 3x, plus c. Part number 2 here. Now in our denominator we do have a radical, and we have, it looks like, some stuff squared under there. So is it possible that this is one of our inverse trig functions? Well, it's looking like it would fit arcsine. And let's go down that path and see how it goes. Here is our a value. A would be 3. 3 squared is 9. And we could look at the next term. Something squared, that something would be x. So maybe our a is 3 and our u is x. But look what's going on in the numerator. If we let u equal x, then du dx would equal 1, and multiply both sides by dx would get du equals dx. So this x would be, a problem, because we don't have a du equals x dx. That x would have to be accounted for. So maybe this isn't arcsine. It kind of looks like it is, especially with that denominator under a radical, a couple of squared things. But if we think back to our natural logs, Maybe u is what's underneath that radical. Maybe u equals 9 minus x squared. If that is the case, then the derivative du would be negative 2x dx. Maybe this will be easier to integrate if we rewrite it as a rational negative exponent. So there's our numerator, and then our denominator we could change into a 9 minus x squared quantity to the negative 1/2 dx. So here is our u value, and our du is negative 2x dx. Well, we have an x dx, so we just need a negative 2 squeezed in there, and of course to balance it, a negative 1/2 out front. So now we have negative 1/2, and we have our indefinite integral. Here is our u to the 1/2 power negative, u to the negative 1/2, and we have our du. So we're ready to go. Raise the exponent by 1 from negative 1/2 to positive 1/2, u to the 1/2, and then divide by that new exponent. Dividing by 1/2 is the same thing as multiplying by the reciprocal, 2. And we'll have our arbitrary constant plus c. So here these will cancel out, and we'll have a negative u to the 1/2 plus c. And we can plug our u value back in now. U was 9 minus x squared. Negative 9 minus x squared to the 1/2 power plus c. And if you want to get rid of that 1/2 power, we could rewrite that as a radical. Negative square root of the quantity 9 minus x squared plus our constant c. So that one we didn't need inverse trig functions for or logarithms for. We did that one with just a basic U-substitution. This third one, they're just asking us the question in a different way. Solve the differential equation. Find the equation of the line that passes through the given point. So here's our differential equation, dy dx equals. If we multiply both sides by dx, we get dy equals 3 over 2 minus x dx. And if we integrate the left side, the integral of the dy is going to be y equals, and then we'll have the indefinite integral of 3 over 2 minus x dx. So first we're going to find the general solution, integrate and have our plus c at the end, and then we're given here an initial condition, a point that the line passes through, or that the curve passes through. So we'll substitute in and find our c value for this and come up with the particular solution. So what method are we going to use to integrate this? Definitely not an inverse trig function. Doesn't look like it's going to be a U-substitution either. Let's try thinking about this as a log. So if we think about our denominator as our u equals 2 minus x. The derivative of that, du dx, would equal negative 1, and then we'd multiply both sides by dx. Du equals negative 1 dx. Do we have a negative 1? No. But what we can do, this 3 by the constant multiple, we could pull that out front. We don't need it. And what we need is a negative 1 dx. Well, I can put my negative 1 to go with the dx, and then that would be my du. But if I do a negative 1 in here, I have to multiply outside by the reciprocal. The reciprocal of negative 1 is negative 1. So that would make that into a negative 3. So now let's do the full u sub. We'll have our negative 3 out front. Antiderivative. Our u is the denominator. Negative 1 dx is our du, or u prime. So it looks like we got all set up for logarithmic. Let me get this out of the way. And when we take that antiderivative, of course it's going to be negative 3. And then the natural log of the denominator, u, which was 2 minus x. 2 minus x, plus our arbitrary constant c. Now we have an initial condition. We know that when we put a 1 in for x, the whole thing is equal to 0. This is our input, a member of our domain. This is the member of the range that is paired up with that x value. So if I take this equation and I substitute in a 1 for x, that becomes a 2 minus 1 in there. plus c, the whole thing is equal to 0. So let's see what goes on. We have negative 3, the ln of 2 minus 1 is 1 plus c. Well, the natural log of 1, I hope you have that memorized by now. The natural log of 1 is 0. So this becomes a 0, which wipes out the negative 3. So we get c is equal to 0. So actually our particular solution is we're basically going to drop the c off. We could rewrite it as negative 3 natural log of 2 minus x plus 0. But we don't need the plus 0. It's nothing on there. So this is our general solution. And this is our particular solution. That is the equation of the line that passes through that given point. So let's see here in example 4. Evaluate the definite integral. And we got 5 over the quantity 3x plus 1. Let's see, definitely not going to be inverse trig stuff there. Doesn't look like it's going to be a U-substitution. It might be another log one. So let's see here. Our denominator is a function, 3x plus 1. What would the derivative of that be? It would be a 3. And, you know, that's just a constant away from what we already have. So let's let u equal our denominator. U is going to equal 3x plus 1. So then du would equal 3 dx. And the integral that we have, we're going from 0 to 4. Our numerator is 5, and then we have our 3x plus 1 dx. Well, the 5 is a constant multiple. We can pull that out front, leaving a 1 up top. But we need a 3 dx. So for our substitution here, we're going to need a 3 dx. And to balance that out, we're going to multiply out front by its reciprocal 1/3. So let's see here now. 5 times a third is 5/3. And we have our definite integral from 0 to 4. We're letting u equal our denominator. And then our 3 dx is replaceable with a du, or in prime notation, that would be u prime. And it looks like we're ready to go. Now here we have a decision. Should we change our upper and lower limits to be in terms of u, or should we substitute back and solve it in terms of x? Actually, why don't we do it both ways? What the heck, twice the fun. So when we integrate here, we're going to have 5/3. And then we're going to have the natural log of our denominator, u. And then we have this as a definite integral from 0 to 4. And now I'm going to substitute back in my U-substitution. So this is going to become the ln, or 5/3. The ln, the absolute value of 3x plus 1 from 0 to 4. So let's see, I'm going to need a little more room here. Let me get rid of this. Oh, actually, I need some of that. Let me just go to the next slide. I'll copy this. So here we are. And we're going to evaluate our upper limit first is going to drop in. So we're going to have 5/3. The natural log of, we plug in that 4. 3 times 4 is 12, plus 1 is 13. Minus 5/3 the natural log of absolute value, plug in our 0. 3 times 0 is 0. We get a plus 1. And there we go. Natural log of 1 is 0. And that 0 times 5/3 wipes all this out. This is now gone. So what we get is 5/3 the natural log of 13. We can drop the absolute value bars because we know it is a positive value. And if we punch that into the handy dandy calculator, you're going to get approximately 4.275. So there we did the u sub, and then we substituted our u back in, and that for the 3x plus 1, and we evaluated the old limits from 0 to 4. Another way to have done this would have been to have changed our upper and lower limits. When we did our u substitution, we could have changed our limits to be in terms of u instead of x. So here again is u equals 3x plus 1. My old limit, lower limit, was a 0. if I plugged a 0 in for this x, I'd get 3 times 0 is 0, plus 1 is 1. My lower limit in terms of u would have been a 1. And I could have plugged my old upper limit of 4 in. 3 times 4 is 12. 12 plus 1 is 13. So my limits in terms of u would have been from 1 to 13. And from here, I would drop in my upper limit in terms of u, and I would have 5/3 natural log of 13 minus, plug in my lower limit of 1, 5/3 the ln of 1. So you can see here we're going to have the same answer. The ln of 1 is 0 times the 5/3 0 is 0. This is wiped out, and we've easily got 5/3 the ln of 13, 5/3 the ln of 13. Let's see number 5 here. It says find the area of the region bounded by the equation. So this is a squared term divided by a first power x term. If we did graph it, it would be a straight line, but we don't even have to graph it. We know it's going to be positive across the interval from 1 to 5, and we're going to find the area bounded by it. So we're going to have a definite integral from our x values of 1 to 5 of the function x squared plus 4 over x dx. Well, let's see, where do we begin? This doesn't look like it's going to fit the inverse trig function stuff. If we look at our denominator as a function x, the derivative would be 1. Our numerator is a far cry from that derivative. But I do see something. We've been talking about this pretty much all year. My numerator is 2 terms. My denominator is a single term. So let's break it up. We have the first term of the numerator over our denominator, plus the second term of our numerator over the same denominator, and dx. And I'd need parentheses to make that official. So it looks like here we can break it up and evaluate a couple pieces separately. So let's see what happens when we simplify each of those terms. Our definite integral is still from 1 to 5. X squared divided by x is x. And then we get plus 1. Oop, and did I mess something up there? That was x squared plus 4. What am I doing? I got to back this all the way up. What was I thinking? This is x squared plus 4 over x dx. And then we break it up into our separate pieces. X squared over x plus 4 over x. Trust me, that's a squared. dx. So we simplify. 1 to 5. X squared over x is x plus, and if we thought that about that as 4x to the negative 1, remember when we integrate would raise power by 1, that would raise us up to 0, and we divide by the new power 0. Can't do that. So we're going to leave it as 4 over x, because that is going to fit logarithmic integration. So let's do each piece independently. When we integrate the first piece, x to the first power, we raise the power by 1 and divide by the new power, x squared over 2. And then we're going to have plus. This is going to be, if we sort of drop the 4 down front, we'd have a 1 up top, and the integral of 1 over x is the natural log of x. And we'd have 4 times that. So it's going to be 4, the natural log of the absolute value of x, and this whole integral will be evaluated from 1 to 5. And we could drop the absolute value bars right now since our upper and lower limits are both positive numbers. So let's see what happens here. Upper limit 5 drops in first. It's going to go in here and be squared. It's going to go in here and be a natural log. So 5 squared is 25 over 2 plus 4 times the ln of 5. That's our first term, our upper limits evaluated. And then we're going to subtract the evaluation of our lower limits. Plug the 1 in for x. 1 squared over 2 is a half. Plus, we plug the 1 in for that x. We're going to have the 4 times the ln of 1. 4 ln of 1. And remember, the ln of 1 is 0. That 0 will be multiplied by the 4 and wipe that all out. So what we have is 25 halves plus 4 ln 5 minus a half. And if we punch that into the calculator, we would get a decimal approximately 18.4378. Let's see, number 6 now. Find the integral. And our numerator is a constant. Down in the denominator we have 1 plus 9x squared. So if we're thinking logarithmic, I'd look at this as my u. What would my derivative of that be? 18x. You know, we have the constant, but we're missing the x. So that's a big problem for logarithmic. We're not going to apparently deal with that. Let's think inverse trig. No radical in the denominator is a dead giveaway. We might be dealing with arctan. So let me put this over here so we can see that arctan formula. Let's see if we can get this to fit into this mold. So our denominator, we need to break it up into squared things. 1 is 1 squared plus we need to write we need to write 9x squared as a quantity, something quantity squared. Well, the square root of 9 is 3. The square root of x squared is x. 3x quantity squared is the same as 9x squared. So it looks like we're going to have an a equal to 1 and a u equal to 3x. So what would our du be? Our du would be 3 dx. Well, we don't have a 3, and we could think about it this way. If we pull the 12 out front, let me give myself a little more room here. You know, we have our 12 in the numerator. That's a constant. By the constant multiple rule, we could pull that down front. And now we want we still have our dx's here. We need a 3 dx. So if I plug a 3 up top, 3 dx to be my du, of course I'd have to balance that with a 1/3 out front. And it looks like we're set up. This 1/3 of 12 is going to be a 4. And then we have our integral. 3 dx is the du that we need by the formula here. Our a value is going to be 1 squared. Plus our u value is 3x. So here's a, here's u. We're all set to go. So when we take this integral, we're going to have 4 from the 4 out front. And now we're just going to fall back to this arctan formula and plug in our a's and our u's in the appropriate places. So the first part is 1 over a. So 1 over a, our a value is just 1 over 1. And then we have arctan. After arctan comes a fraction, u divided by a, or 3x over 1. And we have our plus arbitrary constant c. So when we clean this up, 4, 1 over 1 is 1, we don't even need it. And then we have our arctan. 3x divided by 1 is just 3x plus c. Okay, in number 7 here, we're looking for another indefinite integral, t divided by this quantity under a radical. If I'm thinking, logarithmic or even a U-substitution, I could write that as t, and then this would be 1 minus t to the 4th to the negative half. If this was my u, my derivative would be negative 4 t to the 3rd, and I don't have a t to the 3rd. So it doesn't look like it's going to be a U-substitution. It doesn't look like it's going to be a logarithmic. But we might be able to squeeze it into one of these inverse trig function formulas. So there is a radical in the denominator. I know that eliminates arctan. So it's going to be one of these two. I don't have that extra little u out front. And I do have my number first minus my function. So it looks like it's going to be arcsine. So let me slide this down so we can just see the arcsine formula. And let's see if we can make what we have fit that template. So in the denominator, I do have my radical. And remember, I need something squared minus something squared. Well, 1 squared has got to be 1. What do I square to get t to the 4th? Well, that would be t squared. So I'm thinking maybe my a is 1 and my u is t squared. Well, if u is t squared, then du dt would be 2t, and I'd multiply both sides by dt, and I have du equals 2t times dt. I have a t dt, so I need a 2t dt. So if I put a 2 here, I'd balance it out front with a 1/2. So I'd have my 1/2 out front, and then this 2t dt becomes my du. So I have du. It looks like I'm fitting the formula. I have my du up top, I have some number squared minus some function squared, and I'm ready to integrate. So the 1/2 is going to stay. And then this indefinite integral, I just plug my a's and u's into the arcsine function. 1/2 arcsine u divided by a, or t squared divided by 1, which is just going to be t squared. And I have my plus c, plus my arbitrary constant. All right, one more. Number 8 here. Evaluate the definite integral from root 3 to 3 of this quantity. And my denominator is a function, 9 plus x squared. If I take the derivative, it'd be 2x. I have a constant, but I don't have an x, so it's not going to be logarithmic. I could try to set it up as a U-substitution. We're going to run into the same problem. We'd be missing an x term. So we have a numerator and a denominator with 2 squared terms added together. It looks like it's going to be arctan. So let's see if we can get this to fit into this mold, into this template. Definite integral from root 3 to 3. In my denominator, I want something squared plus something squared. And my 9, well, that's 3 squared. And x squared is x quantity squared. So it looks like by this formula, my a is going to be 3, and my u is going to be x. If u equals x, then du dx would be equal 1, and we'd multiply by both sides by dx and get du is equal to dx. So I can take this dx out right now and replace it with a du. So by the constant multiple rule, I need to get that 6 out of there. I'm going to put the 6 down front, and now I have 6, my definite integral, du over this stuff. It does look like I've perfectly fit into that arctan mold. So we're going to have our 6 stays put, and then we're going to fall into the arctan formula. 1 over a is our first fraction. Here it's going to be 1/3. 1/3 arctan u divided by a, or x divided by 3. 1/3 x. And then, we don't need the plus c because we have a definite integral. So we're going to evaluate this bad boy from the root of 3 up to 3. Get rid of this. And let's clean this leading coefficient up here. 6 times 1/3 would be 6 over 3, or 2. 2 arctan of 1/3 x from root 3 to 3. And to evaluate, we drop in our upper limit first. In goes the 3. So we're going to have 2 arctan of 3 over 3, or 1, minus, plug in our lower limit, 2 arctan root 3 over 3. Okay, now it comes back to a unit circle. We're taking the arctan of a couple things here. So we're first quadrant, we're positive. We're just looking at the first quadrant of the unit circle. Where is the arctan equal to 1? Well, tangent always has a value of 1 at the 45-degree angles or the quarter pies. And in the first quadrant, that is going to be a 1. Root 3 over 3. Now, where does that occur? Root 3 over 3 is the tan value at pi over 6. And we don't need it now, but remember the last tangent in the first quadrant would just be the positive root 3. So a quarter pi has a tangent of 1, a sixth pi has a tangent of root 3 over 3. So we're going to have 2. The arctan of 1 is quarter pi. Minus 2 arctan of root 3 over 3. That arctan of root 3 over 3 is pi over 6. So here we're going to have 2/4 pi, or a half pi. Minus here is going to be 2/6 or 1/3 pi, pi over 6, or pi over 3. And if we subtract those, we get pi over 6. And that's our final answer. Hope you're ready for the test.